record. Feel free to interrupt me anytime, guys, and I appreciate it. I can get kind of caught up in making sure I'm explaining things and doing things right and taking attendance, and got the family in the background walking around trying to go to soccer practice. So there's a lot going on. So I appreciate your input. All right.
Got you.
Pardon me?
I said, we got you. We'll try to help you.
Thank you. Awesome. Thanks, Tabitha. Okay. Back to air temperature. So the hotter the air, the more moisture it can hold. And this is hilarious. So and this always, I like these little stories because they help me to remember why certain things happen. So I had a friend that was like spent a summer in Phoenix. This is when I was back in college, and he came back and, you know, just chatting, whatever. And they're like, he's like, yeah, it's like 110 there. It was miserable. And somebody else said, yeah, but it's a dry heat. So you're not all hot and humid all the time. And he's like, yeah, but so is a microwave. I just thought that was the funniest thing ever. So it's a dry heat, but doesn't necessarily have to be comfortable because it's still really hot. Okay, so psychrometric chart. This is going to be a chart with a graphic representation of all these different concepts coming together, and there's going to be a lot of lines. So we're going to just take it one concept at a time. Okay, so first chart, and I'm going to turn on my little drawing tool here. Draw straight line. I'm going to go for red. So this is half of the chart, just to get started with. So along the bottom axis is the dry bulb temperature, so known as the sensible heat, or I shouldn't say that. Sensible heat only addresses dry bulb temperature. It is regardless of what the moisture content is. So that's along the bottom axis, and going up the right-hand side is our moisture content. And that is as you recall, moisture content can be specific humidity. Okay. Come on. No, you're not. Hold on a second. Okay, I can't do that. Okay, so moisture content is also specific humidity or humidity ratio. Okay, and it's measured in moisture per pound of dry air. Don't have to worry about that too much. It's like a micron of water per pound of dry air, but how do you weigh a pound of air? So it's just when we get into conductance or stuff, it would start to make a difference, but we're not gonna have to worry about it too much. Okay, next thing on this half of the chart. So we have dry temperature, and we have humidity content, and these curves here are our relative humidity lines going up. So the very top line here is 100%. The reason this is curved is that the warmer the air temperature gets, the more moisture it can hold. So it's not a straight line, which would be a direct relationship, but it's a curve because at 85 plus degrees, it holds a lot more volume of water than at, excuse me?
There's an acceleration to the line instead of just.
Yeah, it keeps going up. We don't have to worry about that too much. So more moisture at 85 degrees in volume versus at 40 degrees, the maximum amount of moisture that the air can hold is a lot less volume.
This is a little off topic, but will it always rain at 100% relative humidity? No.
No,
Okay.
it will not. And that's not off topic.
Good question.
Yeah, it's a very good question. No, you can have 100% humidity without it raining. Rain is more of a weather factor than a temperature and moisture factor. Okay, so that's half of the chart. Now, this is the full chart, and I get rid of those lines if I can. Oops. Erase. 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 Awesome. So again, we still have the dry bulb temperature along the bottom, and oops. And the moisture or the humidity ratio going up the right-hand side. We still have our curved lines are our percentage of relative humidity. So we have 90%. This chart doesn't actually say 100%. Top line is 100, and we have 90, 80, 70, 60, down to 20. Okay, so the next thing that's going on here are our horizontal and vertical lines, and actually, they just didn't draw them before. The angled lines going from the top left to the lower right are the wet bulb temperatures. It's where it's taking into consideration what the temperature is and what the moisture content is. And now, this is key. So at 100% relative humidity, the dry bulb temperature will be equal to the wet bulb temperature. That is the only time. That is when no more moisture can be added to the air. So the wet bulb temperature, say it's 110 and 25, actually let's get down to 100 at 25% relative humidity. The air temperature is 100, but the relative humidity is 25. The wet bulb temperature is but just over 70. We got 70 here, we got 75 there. So what that means is 25% relative humidity is pretty low. So even though it feels really hot, there's such low moisture content that wet bulb temperature is just over 70 degrees. What do I have next? Wait, I gotta get out of this. Okay, we're gonna do a couple of practice things here. Take off these lines. Okay, so we're gonna walk through this together. 70 degrees Fahrenheit, dry bulb temperature at 100% relative humidity is 110 grains of moisture per pound of dry air. So let's go back to the chart. So 70 degrees, 100% relative humidity, 110 grains of moisture per pounds of dry air. So we have 70 down here, and we're going to go all the way up to 100% humidity here and follow the line over, gives us exactly 110 grains of moisture per pound of dry air, or our specific humidity, our humidity ratio. Next one, 70 degrees, 50% relative humidity. Back. So we have 70 degrees, and we go up to, I'm going to draw this. First one was easy because we were going all the way up, but 70 degrees up to the 50% relative humidity, and then going over, we're at about 55. Mouse, there's gotta be a keyboard way to do this. Okay, yep, 55 grains. Okay. All right. So to reiterate from earlier, that at 100% relative humidity, the dry bulb temperature will equal the wet bulb temperature. And from those diagonal lines that we saw reading the wet bulb temperature, that unless you're at 100% relative humidity, the dry bulb temperature will always be less than the, the wet bulb temperature will always be less than the dry bulb temperature. So we've got 80 here, unless we're at 80 all the way up here for 100%, this dry bulb temperature is always going to be less. So going down to, let's say, 190, 80, 70, we were at what, 80 degrees? That dry bulb temperature is going to be between 70 and 75. Okay, so it's less than the maximum. Okay, a few more examples. 60 degrees air, that's dry bulb, at 50% relative humidity. If you heat it 10 degrees and you go up to 70 degrees, let's look at how much that humidity changes. It goes from 50 to 38. So we are at 60 down here. Be a better way to do this. Put that over there. So 60 at 50 degrees relative humidity, and then we add 10 degrees to the temperature, so this is a sensible heat gain, the humidity is now less than 40% because we're not adding any additional moisture to the air. So 90 degrees at 80% relative humidity, and we cool it to 75 degrees, it goes to 100% humidity. So that was 95 at, what did I say? Is that 95? Let's say it's up here. I forgot what I just said it was, but we were going from 95 down to 75. Here's 75. Sorry, I got to go back and see what I was saying. 80%, and we cool it to 75. So we got 190, 80, 75. It's right here. Whoa, that's not what I want. Oh, come on. Oh, come on. Try it again. 95 at 80 right here. And we take out 15, all right, 95, 85, 20 degrees. We're down to 100% humidity because we have taken out 20 degrees of sensible heat without removing any moisture, but now our relative humidity is up to 100%. And this is why air conditioners also do dehumidification, because you won't be comfortable at 100% humidity, even at 75 degrees in temperature. And I've got some random things on the screen. Okay. Okay. Let's see. I'm gonna assign a couple of these to you guys real quick. So Marwa and Isabel, and I'm going to take the screen back to this psychrometric chart. In class, I would have passed out paper copies, but I'll just bring it up on the screen. So Marwa and Isabel, if you can look at this first one here, we're going to read the moisture content, 45 degrees dry bulb at 100% humidity. Priscilla and Mars, can you do the next one? What is the relative humidity at 65 degrees Fahrenheit? At that moisture content. Okay. This might be missing information. Hold on a second. Guys, write these down for me, please. Okay, San Diego. Today I did check this out when I set this up a little while ago. It was 61 degrees out earlier, and it was 72% relative humidity. And I don't know if you guys remember when we were talking last week, and I looked up what the relative humidity was, and it was like 17%. So we've gone from like 17% to 72% in a week. So we're looking for the wet bulb temperature. If Dave and Arturo can look for that one, And don't worry about that question. Tabitha and Francis, can you do the first one too? Okay, so we've got Marwa, Isabel, Tabitha, Francis. You're looking for moisture content. Priscilla and Mars, you're looking for, oh, these are related. That's why I wrote it like this. Sorry, once we do this, once we figure out this one, we will know what that moisture content is, and we will read the relative humidity of 65 degrees. And then, was it Dave and Arturo? You're looking at what's the wet bulb temperature for today in San Diego, 72 relative humidity, 61 degrees Fahrenheit. You guys got that? That's clear, right? Okay, so back to the chart. Take a minute. You guys can also draw on here, as we discovered. Okay, Marwa, you're around somewhere. Can you talk to us about the first one?
Yes, of course. For the first one, for the dry bulb temperature, it's 45. It's here. Oh my god, let me draw something. Okay. It's here. And goes up 200. Oh my god. Where's 100? Oh, I went so far.
It's okay.
Yeah, the 100 is here. I don't know if I'm doing correct or not.
Okay, so at 100, you want to stop at the top curved line.
It's here? Okay.
Yep,
Okay.
there you go. And now you do the line over to find the moisture content.
Oh, okay. Like this?
Yep.
Okay. Oh, yeah, between
Yes.
40 and 50. Like 45 also? Okay.
Sure. But yeah.
Yeah.
Okay, so we've got 45 grains of moisture per pound of dry air. So now the second part was to see at that moisture content 45, and I'm going to ask Mars at that moisture content at, I think it was 65 degrees if I recall. And Mars, correct me if I said that wrong.
Yeah, 65.
Okay, so what relative humidity would that be at?
Would it be around here? Oh,
Okay, there's the temperature, and we were at 45 on the humidity ratio. So that's going up the right-hand side. So if you were to draw a line headed left from 45, which curved relative humidity curve would you land on?
this curve?
Nope, you're a little high. So let's go back to,
Would it be
okay.
50%?
Yes.
Thanks.
So that, I hear a voice.
Yeah, so would it be 50%?
Yes. Is that Priscilla? Is that you?
Yeah, it's me.
Excellent. Thank you. Yes, perfect. Yes, so at that moisture content at 65 degrees, it's hitting the 50% relative humidity curve. Okay, Arturo, for San Diego,
We're ready.
you ready? Okay,
It's 51 to 52 degrees, somewhere in there.
okay, wait a minute. I thought we were doing 72 degrees. No, 61
72% relative humidity
humidity,
with
right?
61 degree Fahrenheit gives us a saturation temperature of 51 degrees. 52 maybe?
It's okay. Oh, yes. You're right. We were looking for the wet bulb temperature. So I'm gonna just draw a little line here. Let's say we're 61 to 72, and we're just over the 55 line of
Oh, okay. I went directly lateral instead of following the line up diagonally.
yes. Okay. Yes. So the wet bulb temperatures, these are the ones that go diagonally down from the left to the lower right. So at 50, so yes, the wet bulb temperature today would be 55. If it was 55 degrees and 100% humidity, we would be at a 55 degree wet bulb temperature. Okay, good job, everyone. That's it takes some practice to read these, and don't when you see a psychrometric chart like this, a good one will always tell you what all of these different lines are: relative humidity, dry bulb temperature. See, here's relative humidity here. It tells you the humidity ratio going up the side. And then wet bulb temperature are the diagonal lines coming down from the left to the right. Okay, good job, everyone. Let's see, I think, oops, I gotta go back to the mouse. I think that was all of the in-class exercises. There's gonna be a few of these on next week's assignment. That's why we're practicing now. Okay, moisture content at what we are today. So today, where we were, 61 at 72, 55 degree wet bulb, we're at about 55 grains of moisture per pound of dry air. Okay. Sample class. Okay. Big question here, big picture. And what is the point of all of this? It's all about thermal comfort and what is comfortable. And the first thing I'm going to tell you is that everybody feels a little bit different at different temperatures and humidity. And it can also be a lot on where you live and what you're used to, where you're from. I worked with an Indian woman who was from Mumbai, and she was always cold and freezing, even on like the nicest days, because she was used to like 110 and 95% humidity all the time. So taking our psychrometric chart, there's some ASHRAE, which is the American Society of Heating and Cooling. which governs a lot of the mechanical engineering guidelines in the construction and design industry, has set out some guidelines on what are the common feelings of thermal comfort given different temperature ranges and different humidity ranges. So, super hot, dry weather, over 90, up to 110, but with really low humidity. So we have, if this is 100, 9, 8, 7, 6, 5, 4, 3. So this line here, let me draw the line. This is the 30-degree relative humidity line. So less than 30 degrees, over 90 degrees, it's hot and dry. Now, who remembers what's a good heating or good cooling method in hot, dry, arid climates?
Thermal mass. No?
Cooling.
Okay.
Cooling, hot, dry. You want to add moisture to the air. Did you say something, David? I saw your mouth move.
My mouth moves all the time.
No.
I
All right. Okay. Well, just a quick reminder, it's evaporative cooling. Desert climates, evaporative cooling because it's adding moisture to the air. Okay. I want to accuse you of moving your mouth again. Let's look at the next one. So hot, humid air is above 30 degrees, 30 relative humidity, but you can't get too hot because, and these are still considered comfortable zones. So, but over, this is 60 degrees relative humidity. If it's really hot, between 90 and 105, as long as you stay less than 60% relative humidity, it'll feel hot and somewhat humid. But if you start to go up in humidity, it's going to start to get uncomfortable. Okay. Same thing, a little bit higher humidity, but a little less temperature is warm, humid. Losing the humidity, you start getting back into the dry zone. Moderate. This is what is fairly ideal between 68 and typically it's like 78 degrees, 68 to 78, between 30 degrees relative humidity and less than 70% relative humidity. This is your sweet spot right here. And if you think about it on your thermostat in the summer, you are usually setting your thermostat for air conditioning less than 70. And in the winter, you are setting your heater to be greater than 70. It's a little, you could set it at 80, but I would say, I usually set my heater at around 72. And then we've seen just here in the last week going from 17% relative humidity where it was really dry and it was beautiful outside. That's probably 70-ish. And now it's 60-ish, but a lot wetter. This is what we went through in the last week. So from there to here. Okay, just a guideline, but this is when they're talking about thermal comfort, or ASHRAE is saying what, how they define thermal comfort. These are the various different ranges that are deemed to be acceptable. And in your textbooks, for those of you that are up to date on your reading, one of the concepts they talked about is with natural ventilation systems, being able to tolerate thermal comfort out of the absolute ideal comfort range, in that we need to start being more tolerant of non-perfect conditions when we are dealing with low energy systems, or more sustainable methods for heating or cooling. Okay, back to my mouse and erase. Do. Okay, so quick recap. From Tuesday, we learned about sensible heat and latent heat. Latent heat is the energy to either remove or add moisture to the air. When you put the two of them together, you get enthalpy, which is the sum of both. So now that we've talked about types of heat, methods of heat transfer, conduction, convection, radiation, talked about thermal comfort and temperature, and humidity, getting back to where we were talking about climate from last week. In our different climates, different times of the year, we're going to be either heating or cooling, and making our buildings and spaces thermally comfortable. So there's 4 types of space conditioning. There's heating, cooling. Okay, that's directly dealing with sensible heat. It's either adding or removing heat energy. There's humidification and dehumidification. Those are the ones that start to address the latent heat content, either adding moisture or taking moisture away. Air conditioning, which is our primary method of cooling, is always, when they say air conditioning, that always means it includes some dehumidification, taking water out of the air. There's other types of cooling methods, and there's some passive types. You can do passive cooling, where you're running cool water through a slab or another piece of mass or something. But all that can do is change the air temperature through conduction and convection and radiation. It cannot physically remove moisture from the air. And in fact, you don't want it to condensate on a floor if you're doing passive cooling. So that's when you have to watch your dew point to make sure that you're not creating temperatures where it's going to cause condensation on your flooring. As long as you keep your water temperatures above the dew point, because dew point, the definition is that's the temperature at which condensation occurs. As long as you stay above that, you won't have condensation on your floors if you're doing passive floor cooling.
Why haven't we seen that technology dehumidification, which is ultimately water harvesting, been employed and deployed in more arid regions on a larger scale? Is it too energy intensive to be worth it?
They actually do. What are they called? Water harvesting in arid. They do that. I think you're right. I think it is expensive. And I'm blanking on the name of the technology that does that right now. It's not desalination. It's the other one. I'll have to look it up. I will look that and get back to you.
Desalinization is when they clean
Take the salt.
the
Yeah,
salt
it's
and impurities
they
out of
take
the
salt water and they take the salt out of the water to get fresh water. Yeah, that's not the right word. That's the words that are popping into my head, but that's not what it is. But in arid climates, they do have. It's not as common. I think it's newer technology, although it's not that new anymore, and it's been around a while. It's expensive, I believe, and I think you're right. I think it is high energy. I'll look that up. Okay, so air conditioning includes dehumidification. But there's other, so we were talking about other cooling strategy, passive cooling. That's one type is doing passive floor cooling, which is similar to passive or radiant floor heating, where you run hot water through a tubing system in a slab or in your subfloor. You can have, there's a bunch of different systems that do it, and that's a radiant heating system. So you can do radiant. That's what I was talking about. Was radiant cooling, was running cool water through the floor that will act as a heat sink and take heat out of the air, but does not do the dehumidification. Passive cooling, another method, is like a courtyard with lots of vegetation. Plants are giving moisture off to the air, and so that can help cool down your temperature. If you think of really hot climates, they often have a courtyard, and then the addition of a fountain. And this is where we talked about evapotranspiration the other week, of adding moisture into the air, again, in more dry climates. Okay, so let's see. We talked about thermal comfort, talked about types of space conditioning. The last bit regarding thermodynamics is talking about conductance, resistance, and kind of, I want to say insulation, but the two things that are important to know are thermal conductance, which is the rate of a heat flow through a material per unit of temperature delta. So it's how heat is transferring through conductance. Remember, conductance, convection, radiation. So the heat flow through conduction through an area, which remember is based on square footage, and then the delta T, or the temperature difference. The opposite of conductance is resistance, which we measure and we call R value. And that is the resistance to the heat transfer through a material. And I'm sure you're all familiar with different insulation values. Like if you were to go buy bat insulation at Home Depot or Lowe's, and we talked about fiberglass insulation and rigid insulation the other day when we were talking about heat transfer. So the resistance value of that insulating material, rigid insulation or bat insulation, is measured with the R value, and the higher the value, the higher the resistance is. So R36 is better than R11. This, talking about the rate of heat transfer, this is probably the most technical thing that we're gonna go over probably this whole semester. And I'm not gonna expect you to memorize the formula, mostly because you'll never have to use it, but you do have to learn it for this class. You won't ever have to pull it out of the air, but understanding how it works is important. So if you recall, I believe, I can't remember which class it was, where I was complaining about the way they write BTUs per hour. This is where it really starts to bug me. So our conductance is measured in BTUs per hour times square footage times the delta T, which is measured in, we're always going to do it in Fahrenheit. So delta T is your temperature difference. You're going to have T1 minus T2, whatever those temperatures are, it's going to give you degrees Fahrenheit. So when you're filling this out and you're trying to solve for your heat transfer, which is Q, the way that I like to make sure that I understand what I'm doing, and if I've got all the parts that I need, we need C, which is your conductance value, which is BTUs per hour times square foot times degree Fahrenheit. We're going to take that and we're going to multiply it by your area, which is your square feet, and your temperature difference, your delta T, which is going to be Fahrenheit. So what's going to happen is your square feet and your area are going to cross each other out, and your degrees and your delta T are going to cross each other out. So you're going to be left with your conductive heat transfer is measured in BTUs per hour. So when we were talking about conduction, remember the other day we were talking about how it's based on the area of the material. So you have two dimensions. When we were talking about convection, it started to become three-dimensional, and so it involved volume, okay? And this is we briefly touched on this the other day, the thermal conductivity value of a material and how certain materials are better conductors, like metal is a very good conductor. Glass is not. Air is the worst. This is why we use air for our insulation. Air is resistive to heat transfer, okay? The thermal conductivity of a material, so this is a value that is material specific. You look it up in charts to figure out what it is. And it deals with the thickness measured in inches. So the definition, is this right, of conductance, which is our C here, comes from our thermal conductivity of the material. So you have your material thermal conductivity divided by your thickness gives you your BTUs per hour foot squared degree Fahrenheit. So if you recall back here where we were talking about the units for conductance, we have BTUs per hour foot squared degree Fahrenheit, and to get that we take the thermal conductivity of a material, divide it by the thickness, and this is where you have to watch your units. Is if your thickness is measured in inches, like you're looking at a 1-inch insulated glass unit, that's 1 inch, but your BTUs are in feet squared. You just gotta pay attention to it. It's gonna give you your conductance value. Normally, if we were in the classroom, I would be doing this, going through this on the whiteboard, but I'm not sure the best way to do that here. So it's just a different semester. This is what it is. You don't have to memorize these formulas, but you have to understand when you see them what they mean. Okay, so that's the bulk of the information for today. Let's quickly recap all of these things that are coming together. So we looked at, this week we looked at the methods of heat transfer, conduction, convection, and radiation. We looked at types of heat, which are sensible and latent. Together, they are, when you add them together, that's enthalpy. That's the total amount of sensible and latent heat together. Today, we looked at the psychrometric chart, which is about our dry bulb temperature, our wet bulb temperature, our air temperature, which is the dry bulb, the moisture content in the air, and how those all relate to each other, how air holds different amount of moistures at different temperatures. It all comes together in the psychrometric chart, and you can look up to see where all those different values fall. And certain ones are in the thermal comfort zone, and then there's a lot that's outside of the thermal comfort zone. So then when you get into space conditioning, it's all about treating the space around you to get the temperature and the humidity into that thermal comfort zone. And then the last thing was the conductance and resistance, which is the R value. And that is how heat moves through a material from one side to the other. The chapter in the book is actually pretty good at explaining a lot of this stuff too. I look at it one way, and I know not everyone thinks the same way. So if you're having a really hard time, please read the chapter in the book. It does give a lot of helpful examples. I think it's pretty well written, and it's not hard to read. Okay, so any questions today? Not yet?
For the assignment that is due tonight, that's from lecture 1 and lecture 2, correct?
Correct, correct. And next week's assignment will be based on this week's lectures. Do you want me, I can bring that up. Do you guys have any questions about the assignment? Not yet?
I do.
Yes.
So
Is
there's
it
one, I'm sorry.
Isabel, right?
Yes.
Okay. Do you want me to bring up the assignment on the screen?
Yes, please.
Okay. That will help us. Okay. All right. Here we go. Yes.
So for number 4, I couldn't find anything about the latitude of the axis of rotation angle on the book. I was wondering if you could.
Okay. What the answer is?
Well, at least a hint
Okay.
or something.
The axis of rotation is the angle of the rotation of the Earth. And right now it's 23.5 degrees. And we talked about how that was the wobble. It's not always exactly what that angle is, but that's what it is right now. It does move on the, is it, I forget, 76,000 years it rotates. So the second part of that question is, so if we know what the angle of that rotation is, what latitude is that on the Earth does that match? What latitude is at 23.5 degrees? Remember, we have the equator in the middle, that's at 0, and you go up and you go down, and there's 2 main lines around the Earth at that angle. Does that help?
No. Sorry.
Okay.
Is it talking about the 90 degree?
No, let's go back. That's okay. I am going to open that up and let's go over this. Okay, so we have, you guys are seeing the an Earth on the screen, right? Okay. We have the axis of rotation of the Earth, 23.5 degrees, and it rotates, it wobbles. And then where that the latitude that matches what that rotation is, there's actually 2 names for it. We've got the Tropic of Cancer, which is 23.5 degrees north of the equator, and the Tropic of Capricorn, which is 23.5 degrees south of the equator. And if you draw a straight line all the way through the Earth, that's called the plane of the ecliptic. Does that help? Okay. I'm open to asking questions. I'm not trying to grill you guys on stuff. My goal is to help you learn, okay? Any other questions about the assignment?
I had a question about number 8.
Okay.
How are we supposed to calculate bin hours again? I assumed
Okay.
it was 24 hours times the day it asked, but I wasn't sure if that was right.
That is correct. So in a year, there's 8760 bin hours. That's 365 days times 24 hours. So if I'm not, this is kind of a, and I did this on purpose, this is not, I'm trying to trick you, but I'm trying to make you think that it's 1 week, it's not 1 year. So take 7 days in the week, multiply it by 24 hours in a day. And that's how many bin hours are in 1 week. Remember, bin hours are, and it's kind of a stupid name, but if you think of it like lots of little bins, you take all your weather data and your climate data, and you've got 10 hours of the year that you're at 75% temperature. That's, you know, they put it all in a bin, and then they can compare all these different bins of different data to see what kind of heating and cooling degree days you have in your climate and how that's going to affect your building loads for heating and cooling.
Oh, okay. Wonderful.
It's that's not this lecture, that's the other one. So let's go climate. And having you guys ask me these questions helps me too, because it lets me know what I've gone over too fast or not enough. There's our climate. Oh, it was actually in this one, solar geometry. So we were looking at the climate zone in California, and specifically we looked at climate zone 7 for San Diego. So the heating and cooling loads for a given climate are expressed in heating degree days and cooling degree days. And essentially, these are a summary of bin hours when you're either in heating or in cooling. So here we go. So this little chart we're still in zone 7 here. And if you think of these as your there's all sorts of little bin hours that make up these, where how many are above where it's determined to be thermally comfortable and how many are below. So in our zone, we have more heating degree days than we have cooling days. Okay, so the bin hours make up those heating and cooling degree days. Francis, did that help?
Yeah, that
Okay. Okay. Sometimes I find looking at a chart or a picture helps me visualize it.
Yeah, definitely the visuals help understand it a little bit better.
Great. Okay. Oh, there we go. Okay. Any other questions on the assignment? Or anything that we've gone over the last 2 weeks? Okay. Let's see what's on the schedule for next week. Here's my chart. Envelope. Yes. Okay. Shoot, I forgot to put in which chapters to read. I'll go over that on Tuesday. Okay, so the conductance and the resistance, when we start looking at our envelope and doing, and then looking at load calculations, that's where that information is we're gonna continue to expand on it and start putting it into application. So we'll have more practice with it and it'll start to make a little bit more sense. And then we jump into the really fun stuff, which is the passive systems and the natural ventilation. So that's the fun stuff. This is the stuff you have to learn. This is how you get to be creative. Because that's why you guys are all in architecture school, being creative. Okay. Get your assignments in at some point. And I haven't assigned anything for next week, so have a good weekend. And I'll see you all on Tuesday.
Thank you so much, you too.
Thank you.
Thank you.
Have an awesome time. See you guys later. Bye, David. Okay.